start to the last part of this video series. We had seen how the CD4017 IC works and functions of all its various pins. Link in the description. Kindly watch it if you haven't done so, because we discussed valuable concepts that will be used here. In today's project, we will cascade the CD4017 ICs to allow us build a running light with 25 LEDs as shown on your screen. In fact, you can cascade as many as you want with this method to get even 100 or more LEDs in your chaser circuit. This is the circuit diagram that we will implement on the breadboard today. We haven't included the LEDs to make it simple to understand and explain how it works. Noticeably, you can see two additional components, the two input and gates from 4081 IC. Unfortunately, we could not find that very IC in the nearby store, and ordering it online would take a month or so. We decided to improvise and design two AND gates from 4 transistors. This is the AND gate circuit we will be using. As you can see, the output Y can only become high when both Q2 and Q3 are turned on, and that only happens when both input A and B are driven high. That's worth noting down for later. By the way, we have done a video that exclusively discusses all logic gates, their truth tables, and how you can use only transistors to make them. Do check it out for more information. Link in the description. Back to our main circuit, let's understand how it works first before we can actually construct it. As you can see, pin 3, Q0, of the first counter is connected to pin 15, the master reset pin of the second counter. Q0 of this counter is also connected to pin 15 of the next IC. This sequence continues for all the CD4017 ICs that you intend to cascade. But when it comes to the last counter, its last output, Q0, which is pin 11, is connected to pin 15 of the first CD4017 to complete the loop. We will explain how that works in a second. Notably, the clock-enabled pin of this last counter is permanently connected to ground, meaning it is ready to receive clock signal at any time. Let's start the analysis from the first counter, U2 on the circuit diagram. When the power comes on, U2 is active, while the rest are disabled. Let's see how that is achieved. From part A of the series, we learned that CD4017 IC needs both pin 15 and 13 connected to the ground to be active and start counting with every clock pulse. In this case, pin 13 is connected to the last output pin 11, which is currently low. Its pin 15 is also connected to the last output pin of the last IC in this cascade. That means U2 is ready to receive clock pulse. And since its pin 13 is directly connected to the clock, it starts counting as soon as the power comes on. But what of the rest? Pin 15 of U3 is connected to the first output of U2. This means it will be driven high when U2 starts counting, which resets it. Afterwards, the pin goes low. Likewise, its clock-enable pin is shorted to pin 11, which is currently low. So, U3 is also ready to receive clock pulses, but is that happening? Let's find out. Its clock pin is coming from the output of the AND gate. The input of this AND gate are the clock and pin 11 of the first IC, U2. Since clock is actively high but pin 11 from U2 is still low, the output of this AND gate is also low, which means U3 does not receive clock pulse. It, therefore, does not count. The same thing happens with the last CD4017. It will not receive any clock as long as U3 is inactive or has not counted up to 10. Let's now check a scenario when the first counter is done counting. Will it restart its cycle, or what do you think happens? When the first counter is done counting, its last output goes high, which consequently disabled it since this pin is shorted to its clock-enabled pin. At the same time, the output of the AND gate goes high since its two inputs are now high. This means U2 is put on hold while U3 starts counting, since it is now receiving clock pulses from the AND gate. U3 will continue counting until it gets to the last output, which puts itself on hold as well. Since this last output from U3 is connected to the input of the second AND gate, this gate opens and clock pulse reaches the last IC. Now, both U2 and U3 are on hold while U4 is active and has started counting. When U4 gets to its last output, pin 11, goes high, resetting the first counter, and everything goes to their initial state. All the counters are now ready to start a new cycle. At the beginning of this cycle, only U2 receives clock pulse. Both U3 and U4 have no clock pulses, therefore, not counting anything. That's how the circuit works. Now let's build it on the breadboard. We will use a clock pulse from an LED flasher constructed using 555 timer IC. Watch our previous video on how to build the LED flasher, link in the description. We will use the following components: 3 CD4017 ICs, 2 AND gates from 14081 IC, 1 330 ohm resistor, breadboard, DC power source, 12 volts, jumper wires, clock signal generator. Once again, we used AND gates built from transistors since we could not get the 4081 IC. Place the 3 CD4017 ICs on the breadboard as shown. Ensure all their notches face left for easier connection and to avoid confusion. Connect all their pin 16 to the positive power rail and pin 8 to negative power rail. Complete all other connections as shown in the circuit diagram. This is the completed setup of the whole system without the LEDs connected to the outputs. On the left are our 2 AND gates. You can see their various inputs and outputs as shown. By the way, I have included the 2 LEDs at the output of the AND gates only for visuals. They are not needed for the circuit to work but helpful when troubleshooting in case some went wrong. Let's power the board to test the system before connecting the LEDs. Bingo! You can already tell that the circuit is working by observing the output of the AND gates. As expected, all the AND gates have 0 voltage at the output when the first counter is active. The second gate goes high when the second counter is active, then they both goes high when the last counter becomes active, and the cycle repeats itself. Let's proceed to connecting our 25 LEDs. Please note that the first counter will only have 9 outputs since its last output is already used as a feedback loop. You can, however, use its first output pin. But when it comes to subsequent counters in this cascade, you cannot use their pins 1 and 11. This only leaves you with 8 output pins to use, and the total is 25 for the 3 ICs. In this case, I am using distinct LED colors for every counter, but once again, it is purposely for visuals. Arrange all 25 LEDs on the breadboard as shown. Short all their negative terminals and connect them to the ground through a 330 ohm resistor. Beginning from the first counter, connect its first output pin to the first LED on the far left and follow the sequence rightwards. Do the same for the remaining counters and you are ready to go. Power the board and observe all the 25 LEDs coming on and off sequentially as intended. Increase the clock frequency to make the LED chaser more visually appealing. You can tweak it as you so please to get the best of what you want. Thank you for watching this video until the end. We have more like it on this channel and we will continue to create more for our viewers. Kindly subscribe and turn on that notification bell so as not to miss our new uploads. Thank you once again for your continued support.